Happy Pi Day, everyone. So this is called Pi Day because this is March 14th, or 3/14. So pi being about 3.14 blah, 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 blah. People thought they'd be cute and make 3/14 Pi Day. What I want to show is that every day is Pi Day if you're in the right geometry. Because we can make pi whatever we want. So let's quick take a look at what pi is, or the way that I'm saying when I say pi can be whatever we want, what I mean by that. Physicists do not agree with me that pi is whatever we want it to be. So, we say we have a circle. So here's our circle. When I say pi, I'm really saying the periphery constant. The periphery, like peripheral vision. The boundary. Peripheral constant. A periphery constant. And really, it's the ratio of a circumference, which is the distance around, and not the radius, unless we're doing tau day, to the diameter, which is the distance across. And it's a somewhat remarkable fact that this is the same no matter how we're doing, no matter what size circle we draw. That if we, say, mark that as one radius and try to wrap it around once, there's our one diameter, wrap it around once, inchworm our way around this, twice, 3 times, there's my mark, 3 times and a little bit. So for a circle, if I were to do this precisely, this would be about 3.14159, blah, 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 blah. It goes on forever. I mean, just like square root of 2 goes on forever, honestly. There are other ways of measuring distance, or other ways of looking at circles, though, and that's really what I want to take a look at here. So, for example, suppose we are on a sphere, so kind of like Earth. So this has a certain roundness to it. And now, if I draw a circle on here, remember, what is a circle? A circle is all the points that are a certain distance from some given point. That distance being the radius. So if I mark a point, let's just say North Pole, because it makes it easier to draw, and I draw all the points, say, that far away from it, I'm going to get a line of latitude. And it's this circle that I have here. Well, what is the circumference of the circle? Well, it's however far around that is. And what's the diameter of the circle? Well, we can't burrow right through the earth there. We got to go up and over. Well, what's that ratio going to be? All right, well, let's throw in some extra details here. It's going to end up being convenient if I measure this not by the height, but rather by the angle, the same way that lines of latitude are measured. And so it's also going to end up being convenient if I'm measuring in radians. Normally I don't use radians when I don't need to, but theta is going to be between 0 and pi over 2, 0 being at the North Pole, in which case we don't get much of a circle at all, which is why I have strictly less than, and pi over 2, which is the equator. Beyond that, then the distance is no longer up and over, but rather under. So we can stop at pi over 2. All right, well, the circumference. Let me draw one more line, a bit thinner. I'm going to want to know that distance there. Well, for the sake of simplicity, let's just say this has radius 1. The big sphere has radius 1. All right. So that means that this length is sine of pi. That length is sine of pi, just by opposite over hypotenuse. So that means that the circumference of that circle, which if we looked at it top down, we would see it as the circle with radius sine of theta. And so that radius, or that circumference, is going to be 2 pi times sine theta. And yes, there's a bit of circular reasoning here, all puns aside, because of the pi that I'm using here and the pi that I'm saying is not actually pi. I know it's confusing. Either way, pi being the traditional pi, 3.159 pi is this one. So it's 2 circumference times the radius. So it's the radius being 2 sine of pi. And that gives me that circumference. All right. What about this up and over diameter? Well, if we again look at the circle that we've drawn this in that plane, this is an arc. So this is twice that arc. So that's going to be 2 theta. This is why I chose theta in radians, to make this all so much nicer. That 2 is coming now this time out of that's theta and that's theta. All right, so circumference divided by diameter is going to be pi times sine of theta over theta, which isn't 1. It could be all sorts of things. So, for example, if we're looking at the line of longitude or latitude that is 30 degrees, up toward the top, that's theta equals pi over 6. And so then this ratio is going to end up being pi times sine of pi over 6, which is 1/2 over pi over that, which is pi over 6. That's 1/2 divided by 1/6. There are 3/6 and a 1/2. That means pi is 3. And pi goes from 3, it goes all the way down. If we're at the equator, we're looking at, well, that's radius 2 pi divided by, so for theta equals pi over 2. We're looking at pi times sine of pi over 2, which is 1 over pi over 2. That's 2. Which, of course that makes sense because this around is the same as this around, although we only need to go this far compared to all the way around. So this was, of course that's half of this. So the ratio here is 2. So really pi can be 2 or 3, anything in between. And really sine of pi over pi, that's sine of theta over theta. For this range of theta, that's going to range anywhere from the traditional pi that we know and love, and that's for the North Pole circle of radius 0, so it doesn't actually hit pi, all the way down to 2. So I guess maybe I lied a little bit when I said pi can be whatever you want, but if we're measuring on a sphere, it's going to be between 2 and pi, the traditional 3.14. Could we get bigger than pi? Yeah, but we're going to have to get weird. Hyperbolic weird. So this is the Poincaré disk, named after Henri Poincaré. And this is one of the early, not the earliest, but one of the early forms of the hyperbolic geometry. There's a few things to keep in mind, the conventions here. The sphere is familiar to you. This is considerably less familiar, I recognize. Imagine our universe is just this outer circle. And these circles are evenly spaced. So it's kind of like a really terrible map projection. This distance is the same as this distance, the same as this distance, and I can't really show it anymore. I just got tired of drawing lines, but these keep going. And so moving a little bit out there is really, if I were to move that in, it would sort of grow to be something fairly big here on the inside. What that means is that lines, what are straight lines, which are the path of least resistance, path of shortest distance, for say this point and this point, is not the straight line because it's really expensive in some senses to move straight across there. It's cheaper if we make an arc in and then out. And then as it turns out, the exact arcs that we want end up being circles that are orthogonal or perpendicular to the outer circle. And so our lines really start looking like arcs to our Euclidean eyes, but if you lived in the space, it would be straight. I'm going to try freehanding these as best I can, unless, of course, the 2 points you're trying to connect are opposites of the center of the disk, in which case, yeah, it really is straight, which I'm going to, again, freehand here. So really we have two varieties of lines, ones that are just diameters of the big circle or ones that are arcs like this. Somewhat remarkably, somewhat surprisingly, the circles here, the curves that are all the same distance from a certain point, look like this. It's gonna, let's say it's about here is that point I'm interested in. The circle around it is going to look like a circle as you know and love. The weird thing is that the center feels off-center. The reason being that this distance between there is the same as this distance here because of this terrible map projection idea. That's fairly short, whereas that's much longer. Well, it's much more complicated because I would have to give you exactly how all of these measurements happen and how exactly the stretch factor goes. But because of the way this map projection works, the way this hyperbolic geometry works, pi is actually going to be the ratio of the circumference to the diameter of this circle is going to end up being more than that 3.14159. That will end up being, and there's actually no cap on how big that ratio can be. It comes down to, well, you're wasting a lot of time out here in this circumference. So this really inflates the circumference of what it ought to be compared to the straight shot, so to speak. And keep in mind, this is also a diameter. That little bit is also a diameter, because if I were to extend that out to the outside, yeah, that really is a line running through the center. That's what makes a diameter a diameter. And so maybe I should have drawn that from there. But I mean, there's all these different diameters that look very unline-like. Anyway, and these are all the same length, and then this length though is going to be less than 1 over pi of the circumference all the way around. So in that sense, pi could be anything between 2 if we're looking at the equator of a sphere. It could grow up to be pi for the normal Euclidean case, or it could get even bigger than 3.14159, this ratio. If it could get bigger than that, if you're moving to a hyperbolic space, which is a negatively curved space. There's all sorts of extra geometry I'm leaving out here. For example, this is a curvature 0 space. This is a positively curved space. This is a negatively curved space. Just depending on where the circle is, this ratio gets worse and worse, bigger and bigger. So pi day can be whatever day of the year you want it to be, not January, I guess, since 2 is our lower limit. But February, March, April, May, they're all, pi day is every day, except January. So I thought I'd show you a bit about pi that you had not seen before. Thank you.